Hi guys, this is the EdExcel AS level further maths paper 1 covering the core pure content, and it's from the June 2019 series. Examiner report wise, this 2019 paper was the second sitting of the AS papers. Obviously the first sitting was the 2018 papers. A lot of the content was quite unfamiliar to people, especially modelling questions. A lot of candidates found those questions to be quite challenging. We're also reminded that it is worth remembering that the new specification is fully linear and all prerequisite study should have been completed before sitting this paper, so make sure you know the content inside out before you sit the paper. Question 1. We've got this matrix M 4, -5 to -7. For part A, we have to show that the matrix M is non-singular. Well, if the determinant of this matrix M equals 0, then the matrix is singular. If it doesn't equal 0, the matrix is non-singular. So for part A, what we need to do is find out the determinant of M. So, we have 4 times by -7 minus 5 times by 2. And if we work this out, -28 minus -10, so we have -28 minus -10, that's -18. And this doesn't equal 0, and therefore we can conclude that the matrix M is non-singular. Okay. Now for part B, the transformation T of the plane is represented by the matrix M. The triangle R is transformed to the triangle S by the transformation T. Given that the area of S is 63 square units, we have to find the area of R. First of all, we can find out the area scale factor. The area scale factor is equal to the magnitude of the determinant of M. So we have the magnitude of -18, which is 18. Our area scale factor is 18. And therefore, the area of R, we divide the area of S by the area scale factor to find out the area of R. That's similar to what you'd find at GCSEs. So the area of R, you'd find this to equal the area of S over 18, which is our area scale factor. So we have 63 over 18, which is 7 over 2. Okay, so we have 7 over 2. And now for part C, we have to show that the line y equals 2x is invariant under the transformation T. Essentially, for this question, we multiply this matrix by x and then 2x, the vector, and if we get as a result some multiple of x and then 2x, we can therefore conclude that the line is invariant. Okay? So, we've got our matrix M for -5 to -7. We multiply this by x and then 2x. Remember, we've got our x coordinate and then our y coordinate, remember y is equal to 2x, we were told that in the question. So if we work this out, we have 4 times by x, that's just 4x. And then we have minus 5 times by 2x, that's minus 10x. And then we have 2 times by x. And then we have minus 7 times by 2x, that's minus 14x. So therefore, we have minus 6x and then minus 12x. This is our result of multiplying this matrix with this vector. And what we can do now is take out a minus 6. So we have minus 6 lots of x times by 2x. What we multiplied the matrix by, this x, 2x, is what we get here, except that we have a multiple of that. And therefore, we can conclude that the line is invariant. Okay. Question 1 was concerning matrices. A lot of people found this question to be quite easy. A lot of people did well on this question. But in terms of part A, where we had to show that the matrix M was non-singular, most candidates fully understood what this meant. So what we mean by that is you had to basically compare the determinant to 0. If the determinant equals 0, then the matrix is singular. If it doesn't equal 0, like in our case, the matrix is non-singular. Make sure that you put your conclusion down as well. There was some poor arithmetic with negative numbers seen, and some failed to reach a conclusion, simply stating that the determinant is non-zero. For part B, where we had to find the area, this was done pretty well, but some candidates failed to realise the connection between determinants and area of scale factors. Other people did not take into account the modulus, so they came out with a negative answer. For part C, the main issue here was that people did not know the difference between invariant lines and invariant points, often attempting to solve ax equals x. Question number 2. The cubic equation 2x cubed plus 6x squared minus 3x plus 12 equals 0 has roots alpha, beta and gamma. Without solving the equation, we have to find the cubic equation whose roots are alpha plus 3, beta plus 3 and gamma plus 3, giving an answer in the form pw cubed plus qw squared plus rw plus s equals 0, where p, q, r and s are integers to be found. Okay, first of all, from here we can state the values of a, b, c and d. A is equal to 2, b is equal to 6, c is equal to minus 3, d is equal to 12. We can now find out what alpha plus beta plus gamma is. That's equal to minus b over a. So we have minus b, so we have minus 6 over a. So we divide this by 2, we get minus 3. We can now find out what the pair sum is. Alpha beta plus beta gamma plus alpha gamma, that's equal to c over a. So we have c, which is minus 3, over a, which is 2. We can now find out what the product is. Alpha beta gamma, that's equal to minus d over a. So we have minus d, so we have minus 12 over a, which is 2. So we have minus 6. We will be using these results throughout the question. Now, for this new equation, we've got these roots shown here. And we can first of all find the sum roots, the pair sum and the product to find out a new cubic. So for the sum roots, let's just write this down. So for the sum roots, we add together the three new roots we have. Alpha plus 3 plus beta plus 3 plus gamma plus 3. Okay, so we have alpha plus beta plus gamma plus 9. Alpha plus beta plus gamma, that's minus 3. So we have minus 3 plus 9, which is equal to 6. Okay, so we have alpha plus beta plus gamma, which is plus 9. So we have minus 3 plus 9, which is 6. We can now find out what the pair sum is. So for the pair sum, we have alpha plus 3 lots of beta plus 3, and then we have alpha plus 3 plus lots of gamma plus 3 plus beta plus 3 lots of gamma plus 3. And now we can expand and simplify all this. So for the first two brackets, we have alpha beta plus 3 alpha plus 3 beta plus 9. And then for the next two brackets, we have alpha gamma plus 3 alpha plus 3 gamma plus 9. And for the final two brackets, we have beta gamma plus 3 beta plus 3 gamma plus 9. And if we tidy all this up, you'd find we have alpha beta plus alpha gamma plus beta gamma, and then we have 6 lots of alpha plus beta plus gamma, and then we have 27. Okay, so that's just collecting all like terms. Now, the pair sum here, alpha beta plus alpha gamma plus beta gamma, we've found that to be minus 3 over 2. So we have minus 3 over 2 plus 6 lots of the sum, which is minus 3 plus 27. The result of all this is 15 over 2. And finally, for the product, we multiply those roots together. Alpha plus 3 lots of beta plus 3 lots of gamma plus 3. So we have alpha plus 3 lots of, well, if we multiply these two brackets together, we have beta gamma plus 3 beta plus 3 gamma plus 9. And then if we expand these two brackets together, we have alpha beta gamma plus 3 alpha beta plus 3 alpha gamma plus 9 alpha, and then we have 3 beta gamma plus 9 beta plus 9 gamma plus 27. And if we tidy everything up, we have minus, skipping a step there, we have alpha beta gamma plus 3 lots of alpha beta plus alpha gamma plus beta gamma, and then we have 9 lots of alpha plus beta plus gamma, and then we have the 27, and we know that the alpha beta gamma bit, we found that to be minus 6. So we have minus 6 plus 3 lots of minus 3 over 2, which is the pair sum from before, plus 9 lots of the sum. So we have 9 lots of minus 3. And then we have 27 as well. And if we work this entire thing out, we get minus 21 over 2. So from this, we can find out what the new cubic is. So the new cubic, we have w cubed minus 6w squared, so we reverse the sign of the sum roots, and then we have 15 over 2w. Okay, so we leave the pair sum sign as it is, and for the product we reverse the sign, so we add on 21 over 2, and all this obviously is equal to 0. And then if we multiply through by 2, we have 2w cubed minus 12w squared plus 15w plus 21 equals 0. In conclusion, P is equal to 2, Q is equal to minus 12, R is equal to 15, S is equal to 21. Question 2 is concerning roots of cubic equations. This question was done quite well. Even though it's a fairly new topic, candidates seem to be very familiar with this topic. A lot of people scored very high marks in this question. Essentially, the mistakes made in this question was the mistakes were seen in the manipulation involved, but candidates demonstrated a sound knowledge of the process to be followed. Omission of the equals 0 or use of alternative variables was rare. But overall, very well done to people for attempting this question. For question number 3, we have to show by mathematical induction that for n being a natural number, the sum from r equals 1 to r equals n of 1 over 2r minus 1 lots of 2r plus 1 is equal to n over 2n plus 1. Now, I wouldn't recommend splitting this up into partial fractions, there's just no need. Follow the usual steps in a proof by induction question. The first step is to show that the result is true for n equals 1. So when n is equal to 1, on the left hand side we have the sum from r equals 1 to r equals 1 of 1 over 2 times by 1 minus 1 lots of 2 times by 1 plus 1. Okay, let's just make this line a bit bigger. Okay, and if we work this out, we have 1 over 1 times by 3, which is a third. On the right hand side, we have 1 over 2 times by 1 plus 1, so we have 1 over 3. We therefore see that the left hand side is equal to the right hand side, and therefore, as the left hand side is equal to the right hand side, we can therefore conclude that the result is true for n equals 1. The next step in a proof by induction question is to assume that the result is true for n equals k. So we will now assume that the result is true for n equals k. In other words, the sum from r equals 1 to r equals k of 1 over 2r minus 1 lots of 2r plus 1, that's equal to k over 2k plus 1. And now for our inductive step, we can now see what happens for n equaling k plus 1. Okay, so if we work this out, we have the sum from r equals 1 to r equals k plus 1 of 1 over 2r minus 1 lots of 2r plus 1. This here is equal to the sum from r equals 1 to r equals k. So let's just write that down. We have the sum from r equals 1 to r equals k of 2r minus 1 lots of 2r plus 1 to the power of minus 1. And then we add on the k plus 1th term. So I'm assuming that you're all familiar with that. So we add on 2 lots of k plus 1 minus 1 lots of 2 lots of k plus 1 plus 1. So I'm assuming that you're all happy with this. Now this bit here we can use our assumption step to simplify. This bit we said was k over 2k plus 1. That's from our assumption step here. And then this bit, well, we have 1 over 2k plus 1 lots of 2k plus 3. And now our goal here is to simplify all this to reach something similar to this. And I always think it's helpful if you write down your end goal. What do you want to show? And for us, we want to show that we have something looking like k plus 1 over 2 lots of k plus 1 plus 1. We want to end up with a result which looks like this. So, if we combine these fractions, here we have k lots of 2k plus 3 plus 1 over 2k plus 1 lots of 2k plus 3. And on the top we can simplify that even further. We have 2k squared plus 3k plus 1. And on the bottom we have 2k plus 1 lots of 2k plus 3. And we can now factorize this quadratic. We can factorize that as 2k plus 1 lots of k plus 1. And on the bottom we've got 2k plus 1 lots of 2k plus 3. And happily for us, the 2k plus 1's cancel, so we're left with k plus 1 over 2k plus 3. And the 2k plus 3, that's the exact same as 2 lots of k plus 1 plus 1. So this here is the same as k plus 1 over 2 lots of k plus 1 plus 1. And therefore we see that this result is true for n equals k plus 1. And our final step is the conclusion step, where we write the following. So since true for n equals 1 and true for n equals k, then it's true for n equals k plus 1, and so it's true for all positive integers n. Okay, so hopefully all that makes sense. Question 3 was regarding proof by induction. This was answered very well by a lot of candidates. A lot of candidates seem to know what proof by induction meant. However, the inductive step, where we try for n equals k plus 1, that seemed to be a bit of a challenge for a lot of people. Though many candidates knew the process of needing to add the k plus 1th term to the sum of the k terms, there were some who did not manage to achieve this, instead attempting to add the formula for the sum of k and k plus 1 terms together or similar. So that's talking about this line here. The final accuracy was then achieved most of the time, well done. Although there were many instances where it was lost due to an insufficient concluding statement or failing to show the expression in the exact form. A few candidates did try to prove the result with the aid of the summation formula applied incorrectly to the denominator. Such attempts scored no marks. Question number 4. The line L has equation x plus 2 over 1 equals y minus 5 over minus 1 equals z minus 4 over minus 3. And the plane pi has equation r dot product with the vector I minus 2j plus k equals minus 7. And we have to determine whether the line L intersects pi at a single point or lines in pi, or is parallel to pi without intersecting it. Okay, so with this Cartesian form of L, I think it would be a good idea to first of all write this equation in column notation. So for the line L, we can write that in column notation. We've got R equals minus 2, 5, 4 plus lambda lots of 1 minus 1 minus 3. If you want to write this as a single vector, we have minus 2 plus lambda, 5 minus lambda, 4 minus 3 lambda. And obviously for the plane pi, we've got this over here. And the line and the plane meet if this over here dot product with this normal, and if all this equals minus 7. Okay, so it's the best way of going about this. We replace this R with what we have here. So the lines meet, let's just write this down. The lines would meet if minus 2 plus lambda I plus 5 minus lambda j plus 4 minus 3 lambda k dot product with I minus 2j plus k equals minus 7. So if we tidy all this up, we have 1 lots of this here. So we have 1 lots of minus 2 plus lambda, minus 2 lots of 5 minus lambda, plus 1 lots of 4 minus 3 lambda equals minus 7. So we have minus 2 plus lambda, minus 10 plus 2 lambda, plus 4 minus 3 lambda equals minus 7, and hopefully you can see lambda, 2 lambda and minus 3 lambda cancel. Minus 2 minus 10 plus the 4, that's minus 8. Minus 8 doesn't equal minus 7. We have a contradiction with the left hand side and the right hand side. So there's no point of intersection between the line and the plane. So let's just write that down. We have a contradiction, and therefore there is no intersection between the line and the plane. Okay, and now we can use the dot product, and if the dot product equals 0 between this vector and the normal, if a line is parallel to a plane, it will be perpendicular to the plane's normal vector. Hopefully that makes sense. Let's just write that down. So if a line is parallel to a plane, it will be perpendicular to the plane's normal vector. Okay, hopefully that makes sense. So if you've got your plane and then you've got perpendicular to that plane a line, then the line would be parallel if that line is perpendicular to the plane's normal. Maybe if I draw that out, which I'll do now. So I've tried to illustrate this as best as I can. If you've got your plane, and then obviously here you've got your normal vector, and if you've got your line L, this line in green will be this line will be parallel to the plane if you've got 90 degrees between this normal and that line, and that will only occur if the dot product is equal to 0. And obviously this line is parallel to the vector 1, minus 1, minus 3. So if we dot product that vector with this normal vector, and if we get 0, then we can conclude that the line is parallel to pi. But obviously it won't be in the plane, because we already know that there's no intersection between the line and the plane. Okay, so what we do then is we work out the dot product. We have 1, minus 1, minus 3, which is the this bit over here, and we dot product that with this normal 1, minus 2, 1. If we work this out, we have 1 times by 1 plus minus 1 times by minus 2 plus minus 3 times by 1. Indeed, we get 0. And from this we can therefore conclude that well, let's just write this down. We can therefore conclude that L is parallel to this plane pi, but not in the plane pi. Okay, so but not in the plane. Question 4 was regarding vectors. This question tested geometrical understanding of the intersection of planes and lines. It was quite unfamiliar to a lot of candidates. A lot of people did put the equation into this form over here from this form, which is quite good, but they didn't know what to do with it. But then we talked about what to do. We basically substitute and set the dot product equal to minus 7. Some people forgot to include that minus, but even so, you still got a contradiction. And the problem was they did not know what to do with that contradiction, and that's said over here. When a correct contradiction was achieved, candidates generally did not realize that this eliminated one of the eliminated two of the three given possibilities, and so went on to try to prove that the line and the plane were parallel using the scalar product of directions. Yeah, essentially, if you carry out this dot product, that tells you that the line is parallel to pi, but we know from here that they don't intersect, so they don't lie, so the line does not lie on the plane. So this is another important point. The geometry of the situation was not well understood, but the carrying out of procedures was well done. I always think if you draw a diagram, that helps to explain what's going on. Question number 5. The complex numbers z1 equals minus 2, shown here, z2 equals minus 1 plus 2i, shown here, and z3 equals 1 plus I, shown here. Those are plotted in figure 1 on a Argand diagram for the complex plane with z equaling x plus iy. For part A, we have to explain why z1, z2 and z3 cannot all be roots of a quartic polynomial equation with real coefficients. And of course, a quartic polynomial, we should know, has 4 roots. And those roots will occur as complex conjugates. So essentially, we've got our answer here. Complex roots of a real polynomial occur in conjugate pairs. So a polynomial with z1, z2 and z3 as roots need z2 star, the complex conjugate of z2, and z3 star, the complex conjugate of z3 as roots. Okay? And that makes sense. Those roots are imaginary, so we need the complex conjugates of that. And therefore we'd have 5 roots in total. But a quartic has at most 4 roots, and therefore a quartic can have z1, z2 and z3 as roots. Okay? So I meant to say, so no quartic can have z1, z2 and z3 as roots. Okay, so we have no quartic can have these roots. Okay? And now for part B, we have to show that the argument of z2 minus z1 over z3 minus z1 equals pi over 4. Let's just work that out. For part B, first of all, let's work out z2 minus z1 over z3 minus z1. We have z2, which is minus 1 plus 2i, and then we subtract off minus 2, which is what z1 is. Maybe if I put this in brackets, and then we divide this thing by 1 plus I minus 2. Okay? And this thing over here simplifies to 1 plus 2i over 3 plus I. And with this thing over here, this 1 plus 2i over 3 plus I, of course we'd have to multiply both the numerator and the denominator by the complex conjugate of the denominator. So we multiplied the top and bottom by 3 minus I, like so. And if we work all this out, 1 times by 3, that's 3. 1 times by minus I, that's minus I. 2i times by 3, that's 6i. And then 2i times by minus I, that's minus 2i squared. On the bottom we have a difference of 2 squares. We have 9 minus I squared, and I squared is equal to minus 1. So we have 3 plus 5i minus 2 times by minus 1. Remember, minus 1 is the same as I squared. And then on the bottom we have 9 minus 1. Again, remember, minus 1 is the same as I squared. So we have 5 plus 5i on the top. On the bottom we have 10. We can simplify this to 1/2 plus 1/2 I. That's what this is. And therefore we need to find the argument of this. So therefore we need to find the argument of that. So the argument of z2 minus z1 over z3 minus z1, that's the same as finding out the argument of 1/2 plus 1/2 I. Okay? And to find out the argument of this, that's quite easy. That's the arctangent of 1/2 over 1/2. So we're finding out the arctangent of 1, which is equal to pi over 4. Okay. And now for the next part, we have to show that arctan of 2 minus arctan of a third is equal to pi over 4. Now this is also easy as well. Essentially, this bit over here, for part C, the argument of z2 minus, just remember what is it, z2 minus z1 over z3 minus z1, that is the equivalent of the argument of z3 minus z1 minus the argument of z3 minus z1. And z3 minus z1, this bit here, we worked out before. This is z2 minus z1. So z2 minus z1. That bit we found to be this bit here, 1 plus 2i. So we have the argument of 1 plus 2i, and then this bit over here, we've already found out what that was before. Here, that was 3 plus I. So we have 3 plus I. Okay, maybe if we shade those in, might make it a bit clearer for us. And using the exact same thing that we mentioned before, to find out the argument, that's the arctangent of the imaginary part over the real part. So we have the arctangent of 2 over 1 minus the arctangent of 1 over 3. So we have the arctangent of 2 minus the arctangent of 1/3, which of course, if we work this out, switch to degrees, switch to radians, we have the inverse tan of 2 minus the inverse tan of 1/3. We get pi over 4. Okay, and that's essentially it. And now for part D of the question, a copy of figure 1 labelled diagram 1 is given on page 12. We have to shade on the diagram the set of points of the complex plane that satisfy the inequality z plus 2 being less than or equal to z minus, the modulus of z plus 2 being less than or equal to the mod of z minus 1 minus I. Okay, so where's that figure? So for part D, let's just write that down. We have z plus 2 modded being less than or equal to z minus 1 minus I. And we can rewrite this as z minus minus 2 being less than or equal to z minus 1 plus I. Okay. Now, just as an important point, z minus minus 2 modded equaling z minus 1 plus I modded, this represents a perpendicular bisectors joining the coordinates minus 2, 0 and 1, 1. Okay, and if you go back to the diagram, so the perpendicular bisector of essentially this line here, we're looking for the perpendicular bisector of this line, and here we have, if I add on the coordinates, we have here the coordinates minus 2, 0, and here we have the coordinate 1, 1. And if you think about z2, here we go 2 up, and then sorry, let me just write down the coordinates of z2. That's minus 1, 2. Here we go 2 units up, and then we go 1 unit to the right. Okay, and in terms of going from z2 to z3, minus 1 to 1, we go 2 across, and then 2 to 1, we go 1 down. So maybe if I add this in, we have something looking like this. So we go 1 down, and then we go 2 this way, and hopefully you can see that we have a right angle here, and therefore because of that the perpendicular bisector passes through z2. Okay, hopefully that makes sense, and it makes sense just based on the relationship between z1, z2 and z3. So essentially what I'm saying is, by inspection, the perpendicular bisector passes through z2. Okay, so if I show that, and remember we've got a weak inequality, so we have to show with a solid line, we've got the following. So I've drawn that perpendicular bisector, and if I can change this colour to a grey colour. Now in terms of where we shade, we're looking at, in this question, where this bit is greater than this bit. So in terms of where we shade then, the region we don't want is all here. So if I can sort of do that neatly, best of my ability, we have something looking like that. Okay, hopefully all that makes sense. Okay, so all this is the region we don't want. Okay, maybe if I make this neater, yeah, we have something looking like that. Okay, let's just join all this up. Yeah, something like that. That'll do. Sort this blob out. We have that. Question 5 was concerning complex numbers. This was quite a challenging question. For part A, where we had to explain this over here, a lot of people did not realize that we had to talk about complex conjugates, and because we've got a quartic polynomial, we needed 4 roots, but if we go through the question, you'll realize that we have 5 roots, so therefore all these cannot be roots of the quartic polynomial. In terms of what else was said, for part B and C, where we had to use our argument knowledge, a lot of people did not know what to do in this. For the first part, a lot of people were confused by the complex conjugate bit over here where we multiply by the conjugate. A lot of people use decimals, which was incorrect, and that was over here for part C. And that's basically it. But there were a couple of attempts using vectors or triangle geometry to try to establish the result, but you can have a read through of why people did not do that question well. And for part D, a lot of people did not realize that we had to talk about the perpendicular bisector. Common errors included lines passing through 0 and candidate strong circles, but I thought it was quite obvious as to why you had to use the perpendicular bisector. It was a fairly standard question, and I think this question, if you know the textbook pretty well, then this question is actually quite easy to do. Question number 6. An art display consists of an arrangement of n marbles. When arranged in ascending order of mass, the mass of the first marble is 10 grams. The mass of each subsequent marble is 3 grams more than the mass of the previous one, so that the rth marble has a mass of 7 plus 3r grams. For part A, we have to show that the mean mass in grams of marbles in the display is given by 1/2 lots of 3n plus 17. Well, obviously, this statement of the rth marble having mass 7 plus 3r makes sense. It's just a linear sequence. We start off with 10 and then we add 3 each time, so we have 3r, and then to find the first term we have 10 minus 3, which is to find the 0th term we have 10 minus 3, which is 7. So that bit is just a linear sequence. Now, when we talk about finding the mean of something, typically when we find the mean, we add up all the numbers and divide by how many they are. That makes sense from GCSEs. So what we have to do to find the mean, if I write this down, for part A, to find the mean x bar, this is equal to, well, we have to add up all the masses together. Now we don't know for definite how many masses there are, at least in part A, so we have to add up all the marbles together. So we have the sum from r equals 1 to r equals n of 7 plus 3r, and then we divide by how many there are. There's n marbles, so we divide by n. Hopefully that makes sense. And for us to show that this result leads to this result, we would have to just use a bit of summation theory. So we have 1 over n being multiplied by 7 lots of the sum from r equals 1 to n of 1 plus 3 lots of the sum from r equals 1 to r equals n of r. Hopefully all that makes sense. So we have 1 over n lots of, well, we have 7 times by this sum, which is n, and then we have 3 lots of this sum, the sum from r equals 1 to r equals n of r, that's n over 2 lots of n plus 1 you should all be familiar with how this bit is the same as this bit, and how this bit is the same as this bit here. Okay? And the rest of it is just simplifying all this. Well, happily for us, if I multiply 1 over n into this bracket, the n terms cancel, so this cancels with this, and then this also cancels with this. So we have 7 plus 3 over 2 lots of n plus 1. So we have 7 plus 3 over 2 n plus 3 over 2. And if we work this out, we have 3n over 2 plus 17 over 2. And if I factorise out the 1/2, we have 1/2 lots of 3n plus 17, which is exactly what we wanted to show. Okay. And now for part B, given that there are 85 marbles in the display, we have to use the standard summation formula to find the standard deviation of the mass of the marbles in the display, giving an answer in grams to 1 decimal place. Now, for part B, first of all, you have to know what the standard deviation is, and if you go in the formula book, somewhere in the formula book, I'm not sure where, I think it's under the A-level maths section in the formula book, under the statistics section. Ah, yeah. We have here the formula for standard deviation. And if I write that down, the standard deviation is given by the sum of x squared over n minus the square of the mean, square rooted. Okay. Now, we can first of all work out what this bit is. Well, actually, before we do that, we can work out what the mean is. We already know the formula for the mean. That's 1/2 times by 3n plus 17, and we know that there's 85 marbles. In other words, n is equal to 85. So we have 1/2 lots of 3 times by 85 plus 17, and if we work this out, 3 times by 85 plus 17 and then divide by 2, we get 136. So the mean is 136. And now this sum from the sum of x squared, essentially we know what x is. X over here is 7 plus 3r, if you want to think of it like that. So perhaps if we do this in a different colour, we have the sum from r equals 1 to r equals n of x squared, which in this case is 7 plus 3r squared. So this bit corresponds to this bit here. That is the same as the sum from r equals 1 to r equals n of 9r squared plus 42r plus 49, which for us, we can happily see that we have 9 times by the sum from r equals 1 to r equals n of r squared plus 42 lots of the sum from r equals 1 to r equals n of r plus 49 lots of the sum from r equals 1 to r equals n of 1. And the sum from r equals 1 to n of r squared. In the A-level maths section that's given here, we can now use this formula as well. So we have 9 multiplied by 1/6 n lots of n plus 1 lots of 2n plus 1, and then we have 42 lots of 1/2 n lots of n plus 1, and then we have 49 n. So a sixth times by n, a sixth times by 9, that's 3 over 2. So we have 3 over 2 lots of n plus 1, 3 over 2 n lots of n plus 1 lots of 2n plus 1, and then we have 21n lots of n plus 1, and then we have 49n. And if we plug all this into our standard deviation formula, then we therefore have the standard deviation. So hence the standard deviation is given by well, we have that bit which over here, so we have 3 over let's write this out properly. What do we have? Sorry, I've lost my train of thought. We have 3 over 2n lots of n plus 1 lots of 2n plus 1 plus 21n lots of n plus 1 plus 49n divided by n minus 136 squared, square rooted. So this bit I need to square root. So that's what the standard deviation is. And hopefully you can see also that this n, and this n cancel with this n. So we can say that the standard deviation is equal to 3 over 2 lots of n plus 1 lots of 2n plus 1 plus 21 lots of n plus 1 plus 49 minus, is it 49? It's supposed to be 40. And then we subtract off 136 squared. Okay, square rooted. And we know that n is equal to 85. So when n is equal to 85, we have the standard deviation equaling 3 over 2 lots of 85 plus 1 lots of 2 times by 85 plus 1 plus 21 lots of 85 plus 1 plus 49 minus 136 squared. Okay, and if you stick all this into a calculator, I've written down the answer, we get 73.559 etc. So therefore the standard deviation is equal to 73.6 grams to 1 decimal place. Question 6 was concerning summation formulas and means. For you to do this paper, you have to know your AS level stats pretty well. And this is what's meant in this examiner's report. Make sure that you know your regular A-level maths pretty well before you do this paper, because a lot of these questions are based upon your regular A-level maths. The first part was answered pretty well, most knew what to do, but a lot of people did not realize what is meant by a mean. You have to divide by the number. You add up all the numbers, so that's why you've got the sum bit, and then you divide by how many they are. That's why I've got the 1 over n bit. So a lot of people fail to show an understanding of what's meant by a mean. Part B, that was quite a demanding question. Obviously you had to go to the formula book because it says use the standard summation formula, and that's in the formula book. You should know it's in the formula book. But they didn't understand what it actually meant on how to use this. People found calculating the mean to be quite tricky. All you just have to do is just sub 85 back into here to find out what the mean is. A lot of people did not relate the sum of x squareds to this bit here, and that's how they came across a lot of the errors. A lot of people used the calculator to find out the mean, to find out the standard deviation, which was completely incorrect. The question says use the standard summation formula to find the standard deviation. So overall, a very difficult question. Question number 7. We've got f of z, which is equal to z cubed minus 8z squared plus pz minus 24. P is a real constant, and given that the equation f of z equals 0 has distinct roots, alpha, beta, and this bit over here, alpha plus 12 over alpha minus beta, we have to solve completely the equation f of z equals 0 for part A. Well, first thing I like to do is label the values of A, B, C and D. So A is equal to 1, B is equal to minus 8, C is equal to P, D is equal to minus 24. And therefore, for part A, we can find out the sum of roots, which will enable us to find out the values of alpha and beta. So if we use the sum of roots, so if we add up the roots, alpha plus beta plus alpha plus 12 over alpha minus beta, we know that this is equal to minus b over a, so we have minus 8 over a, which is 1, which simplifies to 8. And hopefully you can see that the betas cancel out. So we have 2 alpha squared plus 12 over alpha equals 8. We can form a quadratic in alpha for this. We have 2 alpha squared. We have 2 alpha. If I multiply through by alpha, we end up with 2 alpha squared minus 8 alpha plus 12 equals 0. And if I divide through by 2, so maybe if I show this, if we multiply through by alpha and then divide through by 2, we end up with alpha squared minus 8 alpha plus 6 equals 0. And if we solve this quadratic equation, we see that alpha is equal to 2 plus minus root 2 I. And therefore, we have a complex conjugate. So z12 is equal to 2 plus minus root 2 I. And we can find out the third root by substituting back into here. Now it doesn't matter what alpha and beta are. Well, here we can say alpha is equal to 2 plus root 2i. Obviously the complex conjugate part, that'll be beta. We can say beta is equal to 2 minus root 2i. Obviously those being the 2 roots. So the third root, therefore, that will equal, well, if we substitute everything into this other root, we have 2 plus root 2i plus 12 over 2 plus root 2 I minus 2 minus root 2 I. And if we work this out, it's easier to do it on the calculator. First of all, we need to go to the complex mode, and if we type all this in, we have 2 plus root 2 I, close brackets, plus 12 over 2 plus root 2 I, minus 2 minus root 2 I. We end up with 4. So therefore our three roots, we have 2 plus minus root 2i and 4. And now for part B, we have to solve, well, we have to find the value of p. Well, we know that one of the roots is 4. And for us to find out the value of p, that's quite easy. We can just use the factor theorem, because we know that one of the roots is 4 to the equation f of z equals 0. Perhaps if I actually write that down, we can say that the roots of f of z equals 0 are 2 plus minus root 2 I and 4. And therefore for part B, if we actually set f of z equal to 0, if we set f of 4 equal to 0, because one of the roots is 4, of course using the factor theorem, we have 4 cubed minus 8 lots of 4 squared plus p lots of 4 minus 24 equals 0. So we have 4p minus 88 equals 0. P is equal to 22, and therefore f of z is equal to z cubed minus 8z squared plus 22z minus 24. Okay, and that's essentially it. Question 7 was concerning the roots of polynomials. It was answered quite well, because there was a similar question in the specimen paper. For part A, that required the sum roots to eliminate beta, but some people couldn't eliminate beta for some reason, but that was quite rough. The information was a common first step rather than identifying only that which was needed. A lot of people found the correct quadratic, which was good. Some people made algebraic errors, but overall finding the quadratic was done pretty well. But they failed to realize what to do with the two roots they found, and what we mean by that is they failed to find out the third root. I think because you've got your roots in complex conjugate pairs, finding the third root's easy. You just substitute that back into here. Other people found a longer method. You could find the third root with some different methods to what's shown here. Some of whom did not realize that they had to find the two different roots already. Yeah, so there were a couple of ways to do this, actually, in all honesty. You could use the sum roots as well. Part B, where we have to find p, that proved to be quite challenging to a lot of people, surprisingly. The easiest way was the factor theorem, but that was quite rare. You could also use this z minus alpha, lots of z minus beta, lots of z minus gamma, to find a correct cubic and then compare that to p. But that was common, but a lot of people struggled with that because it was quite demanding on the algebra. The factor theorem was by far the easiest method to use. Question number 8. A gas company maintains a straight pipeline that passes under a mountain. The pipeline is modelled as a straight line, and one side of the mountain is modelled as a plane. There are access ways from a control center to two access points on the pipeline. Modeling the control center as the origin or the two access points on the pipeline have coordinates p minus 300, 400, minus 150 and q with coordinates 300, 300, minus 50, where the units are meters. For part A, we have to find a vector equation for the line PQ, giving an answer in the form r equals a plus lambda b, where lambda is a scalar parameter. Well, for us to determine the vector equation, we first of all have to find out what the vector PQ is. So for part A, the vector PQ, that's equal to OQ minus OP. So we have 300I plus 300J minus 50K, that's P, minus 300I plus 400J minus 150K. If we work this out, we get 600I minus 100J plus 100K. And therefore, we can conclude that the vector r is equal to p minus 300, 400, minus 150 plus lambda lots of 600 minus 100 and 100. For part B, the equation of the plane modelling the side of the mountain is 2x plus 3y minus 5z equals 300. The company wants to create a new access way from this side of the mountain to the pipeline. The access way will consist of a tunnel of shortest possible length between the pipeline and the point M with coordinates 100, k, 100 on this side of the mountain where k is a constant. We have to find, for the first part of part B, the coordinates of the point at which this tunnel will meet the pipeline and then the length of this tunnel. So far we already know the equation of the plane. The equation of the plane, that's given by 2x plus 3y minus 5z equals 300. We know that M lies on the plane, so using the coordinates of M has coordinates 100, k, 100. If we use these coordinates, knowing that this point lies on the plane, substituting into this equation, we have 2 lots of 100 plus 3 lots of k minus 5 lots of 100 equals 300. So we have 200 plus 3k minus 500 equals 300. 3k is equal to 600, and therefore k is equal to 200, and therefore M has coordinates 100, 200, 100. Now, the next part of this question is quite tricky to think about. We've got our plane, we've got this point M, which lies on the plane, and we want to find out the shortest distance from this point M to the line X to the line L. And that shortest distance will be from M to a general point on the line X. And that distance between M and the line is perpendicular to the line. Perhaps if we draw this out, it would make a bit more sense. So we've got our plane that's shown here. We've got our line that's shown in red, and then we've got the coordinates of P and Q. And we've got this point M. M here has coordinates 100, 200, 100. M lies on the plane. And we want to find out essentially the shortest distance from M to the line. And that shortest distance is here. And what you'd find is for a shortest distance that essentially for the shortest distance we have a right angle between this point here, between this line here and the vector equation. And if we call this point X, X would have coordinates minus 300 plus 600 lambda, 400 minus 100 lambda, minus 150 plus 100 lambda. And essentially, when we look at this question, for the first part, when we find the coordinates of the point at which the tunnel will meet the pipeline, that's the coordinates of X which we need to find. And then when we talk about the shortest distance, that's finding out the distance mx. Now, we know that mx is perpendicular to PQ. So what we can do with that then is, first of all, find out mx and then set the dot product between mx and pq equal to 0 to find out what lambda is, and then substitute that value of lambda back into here to find out the coordinates of x. So let's write this down. If x is a general point on the line, okay, then we can find out what mx is. Mx is equal to, well, if I write this out in full, mx is equal to OX minus OM. So OX, that's equal to minus 300 plus 600 lambda, 400 minus 100 lambda, minus 150 plus 100 lambda. And OM, that's 100, 200, 100. And if we work this out, we end up with minus 400 plus 600 lambda, 200 minus 100 lambda, and then minus 250 plus 100 lambda. Okay, and for the shortest possible length, mx has to be perpendicular to PQ. Okay, so for the shortest possible length, which is this bit in grey. Let's just write this down. For the shortest possible length, this thing over here, mx, let's just write that down, minus 400 plus 600 lambda, 200 minus 100 lambda, minus 250 plus 100 lambda, this dot product with what we have for PQ, which we found to be this thing here, 600 minus 100, 100. This must equal 0, because we see that mx is perpendicular to PQ. And now we can find out what lambda is, which I'll do now. So we know here that lambda therefore is equal to 3/4, and I've shown the working here. And knowing that lambda is equal to 3/4, we substitute that value of lambda back into here to find out the coordinates of x. So OX, the vector OX, that's equal to minus 300 plus 600 times by 3/4, 400 minus 100 times by 3/4, minus 150 plus 100 times by 3/4. You'd find OX to equal 150, 325, and minus 75. And therefore the coordinates of x would be 150, 325, minus 75. And now when we come to find the shortest distance, we need to find out what mx is. And mx, we substitute lambda back into here. So mx, you'd find that to equal minus 400 plus 600 times by 3/4, 200 minus 100 times by 3/4, and minus 250 plus 100 times by 3/4. So mx therefore is equal to 50, 125, and minus 175. So the distance mx, that's quite easy to find. We have 50 squared plus 125 squared plus minus 175 squared, all square rooted. And if we work this out, we get approximately 221 meters to 3 significant figures. Okay. Now for part C, it is only practical to construct the new accessway if it will be significantly shorter than both of the existing accessways OP and OQ. We have to determine whether the company should build the new accessway. Well, for this we just have to find out the length of OP and OQ and then compare that with what we have already. That is mx. So if we find out what OP is, for part C, OP, that's equal to minus 300 squared plus 400 squared plus minus 150 squared square rooted. And if you work this out, you get a value which is approximately equal to 522 meters to 3 significant figures. And OQ, that's equal to 300 squared plus 300 squared plus 50 squared square rooted. You'd find this to be approximately equal to 427 meters to 3 significant figures, and therefore we have the following conclusion to make. So the new tunnel length is significantly shorter than these values, so it's likely that the company will decide to build the accessway. And now we have to suggest one limitation of the model. We have the following conclusion. So the mountainside is not likely to be flat, so the plane may not be a good model, and that's it. Question 8 was regarding modelling with vectors. That was quite difficult. For part A, people found out the correct equation, but some candidates neglected to start their equation properly with r equals as stated in the question over here. Part B, a lot of people first of all misunderstood what was meant by shortest distance, and we discussed what that meant through drawing a diagram. And if you actually do draw a diagram, that would help to answer this question. Some people failed to find the value of k by substituting into the equation of the plane. I thought that was quite an easy mark to get. Basically, the problem here was candidates did not check carefully what was asked to make sure that they were getting the question right for this part of the question, and details of that are given. The correct distances of OP and OQ were found, but they did not give a correct comparative reason. And for part D, when we talk about the limitations, that was done pretty well. People were talking about the tunnel might not exactly be straight, or the plane might not be exactly flat, and that's the limitation, but some refer to the actual measurements being a limitation, which wasn't correct, and you can read why that was, because that does not affect the interpretation of the model. Question number 9. We've got f of x, which is equal to 2x to the power of a third plus x to the minus 2 over 3, where x is greater than 0, and a finite region bounded by the curve f of x, the line x equals 1/8, the x-axis, and the line x equals 8, is rotated through theta radians about the x-axis to form a solid revolution. Given that the volume of the solid is formed, formed is 461/2 units cubed, use algebraic integration to find the angle theta through which the region is rotated. Well, first of all, you have to notice the following. We rotate through the x-axis, and typically if we rotate by 2 pi radians about the x-axis, the volume is given by pi lots of the integral of y squared dx. Let's just write that down. So if it's rotated by 2 pi radians about the x-axis, then the volume is pi lots of the integral of y squared dx. And you'll notice this pi is half of this 2 pi. I think that's quite important to see. This 2 pi is double this pi, or this pi is half of that 2 pi. And therefore, if it's rotated by theta radians about the x-axis, then the volume is theta over 2 lots of the integral y squared dx. So this and this match up in accordance with this. Theta over 2 is half of theta. And if you can get that far, then the rest of the question is quite standard. We know that y is equal to 2x to the power of 1/3 plus x to the power of minus 2/3. And therefore, if we work out what y squared is, y squared, that's equal to 2x to the power of a third plus x to the minus 2 over 3 lots of 2x to the power of a third plus x to the power of minus 2 over 3. And if we work this out, this is equivalent to, well, 2x to the third times 2x to the third, that's 4x to the 2/3. And then we've got 2x to the third times by x to the minus 2/3 twice. So we have 4x to the minus 1/3. Just make sure that you know your rules of indices for this same base number, and we multiply, we add the powers, and then x to the minus 2/3 times x to the minus 2/3. That's x to the minus 4/3. And we can now substitute this y squared into this formula here, and we can set that equal to 461/2. So we have theta over 2, lots of the integral from x equals 1/8 to 8 of y squared. So we have 4x to the 2/3 plus 4x to the minus 1/3 plus x to the minus 1/3 dx. And we know that this is equal to 461/2. We were told that in the question. We were told that here. And therefore, we can work out this integral to find out what theta is. So, first of all, the halves cancel on both sides. So we have theta multiplied by this bit here. Now if we integrating 4x to the 2/3, we end up with 12x to the 5/3 over 5. And then integrating 6x to the minus 1/3, we end up with 6x to the power of 2/3. And then integrating x to the minus 4/3, we end up with minus 3x to the power of minus 1/3. So we need to work this thing out between the limits x equals 1/8 and 8, and we know that this will equal 461. Remember, here the halves cancel. So we have theta lots of, for the upper limit, we have 12 lots of 8 to the 5/3 over 5 plus 6 lots of 8 to the 2/3 minus 3 lots of 8 to the power of minus 1/3. So that's what we have for the upper limit. And for the lower limit, we have 12 lots of 1/8 to the power of 5/3 over 5 plus 6 lots of 1/8 to the power of 2/3 minus 3 lots of 1/8 to the power of minus 1/3. Okay, so this is what we have for our lower limit, and then we close the brackets, and this is equal to 461. So for the upper limit, if we work out what the upper limit is, we have 993/10. For the lower limit, we have minus 177/40. And obviously this is equal to 461. So we have 41490. 4149 theta over 40 equaling 461, and therefore theta we can find out to be 40/9 radians. Okay, so that's it. Question 9 was concerning volume of revolution. That was done pretty well, but a lot of candidates did not realise that they had to scale the angle, and we talked about that over here. Some people did not realise that they needed to find y squared, but I think if you know your formula for volume of revolution, it's quite easy as to why you have to use y squared. A lot of people used calculators to find out the limits, which was incorrect. We had to use, as stated in the question, algebraic integration to find out the limits. So we had to show this, the full thing of us adding 1 to the power and then dividing by the new power. But the main issue was using theta instead of theta over 2. That was the biggest problem, and we discussed that at the start of the question. Question number 10. The population of chimpanzees in a particular country consists of juveniles and adults. Juvenile chimpanzees do not reproduce. In a study, the number of juvenile and adult chimpanzees were estimated at the start of each year. A model for the population satisfies the matrix system Jn plus 1 and An plus 1 equals A 0.15, 0.08, 0.82 lots of Jn, An, where n is equal to 0, 1, 2, etc. A is a constant, and Jn and An are the respective numbers of juvenile and adult chimpanzees n years after the start of the study. For part A, we have to interpret the meaning of the constant A in the context of the model. Well, A is the proportion of juvenile chimpanzees that survive and remain juvenile chimpanzees the next year. And the reason we say that, the next year's number of chimpanzees depends on the previous years. And all over here in this matrix, we've got numbers less than 1, so the numbers next year will be less than the previous year. And that's why we have a proportion. And obviously we must talk about how when we multiply this matrix with this vector together, A would represent the number of the proportion of juvenile chimpanzees that survive and remain. So the fact that a constant is multiplied by this number tells us that chimpanzees remain for the next year. So that's quite important. And now for part B. At the start of the study, the total number of chimpanzees in the country was estimated to be 64,000, according to the model. After 1 year, the number of juvenile chimpanzees is 15,360, and the number of adult chimpanzees is 43,008. Now, for part A, we have to find the inverse matrix. Now, first of all, we'd have to find the determinant. And to find the determinant, we multiply the A by the 0.82 and we subtract off the product of 0.15 and 0.08. So for the first part of part B, the determinant is equal to A lots of 0.82 minus 0.08 lots of 0.15. So we have 0.82 minus 0.012. So when we talk about the inverse of A 0.15, 0.08 and 0.82, well, we have 1 over the determinant, so we have 1 over the 0.82A minus 0.012 multiplied by the transpose of this matrix. So we swap the A and the 0.82, and then we have the minus of 0.15. So we have minus 0.15 and minus 0.08. So this is our inverse matrix. And now for the next part, we have to hence or otherwise find the value of A. Now, we were told already that at the start of the study, the total number of chimpanzees was estimated to be 64,000. And the start of the study is when we have J0 and A0. So we have A0 plus J0 equals 64,000. Okay. And we know that after 1 year, the number of adults, we were told, is 15,360. Sorry, the number of juvenile is 15,360, and the number of adults is 43,008. So if we substitute that back into here, we can then form a simultaneous equation. So using that, we have 15,360, 43,008, and this is equal to A 0.15, 0.08, and 0.82. And we multiply this by J0, A0. Okay, so we can form two equations from this matrix here. We have A times by J0. So let's just write this down. We have A times by J0 plus 0.15 times by A0. Okay, and this is equal to 15,360. And then we have 0.08 times by J0 plus 0.82 A0, and this is equal to 43,008. So if I call this equation 1, this equation 2, and this equation 3, we can solve these equations simultaneously to find out what A is, what A0 is, and what J0 is. So from equation 1, hopefully you can see that A0 is equal to 64,000 minus J0. We'll call this equation 4. And we can now substitute in equation 4 into equation 3 to find out what J0 is. So if we substitute in 4 into 3, we have equation 4 here and equation 3 here. So we have 0.08 lots of J0 plus 0.82 lots of 64,000 minus J0, and this is equal to 43,008. Okay, so if we tidy all this up, we end up with minus 0.74 J0 equaling minus 9472. So therefore J0 is equal to 12,800, and A0, if we substitute this back into equation 4, A0 is equal to 51200. And from this we can substitute these values back into equation 2. So now sub back into equation 2, we have A lots of 12800 plus 0.15 lots of 51200. Make this clear. and this is equal to 15360. So we have 12800A equals 7680, and therefore A is equal to 0.6. And now for the third part, we have to calculate the change in the number of juvenile chimpanzees in the first year of the study according to the model. Well, initially, we already know that J0, the initial amount of juvenile chimpanzees in the population, that's 12800. And we know that in year 1, that's 15360. And therefore, the change in the number of juvenile chimpanzees, we have 15360 minus 12800. We end up with 2560. Okay. Now for part C, given that the number of juvenile chimpanzees is known to be in decline in the country, we have to comment on the short-term suitability of the model. So one thing that's important is that the number of chimpanzees is known to be in decline in the country, and we calculated in the first year the number of juvenile chimpanzees is increasing, which is contradicting that statement. So we can say that the model is not suitable because as the number of juveniles has increased, the model is not initially predicting decline. Obviously it's increasing, and therefore it's not suitable in the long term, because we know in the long term the number of juvenile chimpanzees is known to be in decline in the country, the decreasing. And now for part D, a study of the population revealed that adult chimpanzees stop reproducing at the age of 40 years. We have to refine the matrix system for the model to reflect this information, giving a reason for your answer. Now, I think this question, even though it's worth 2 marks, I think it's probably the most difficult question on the paper. It took me a very, very long time to figure out what the mark scheme was saying and how to best explain what the mark scheme was saying. So I'll write out the answer and then we can discuss it. So I've written out the answer and I think it's a good time to explain it. If we say M is the number of mature chimpanzees n years after the start of the study, when we talk about mature, the definition of this, we're talking about those who are those who stop reproducing and at the age of 40 years old. So this is what we talk about, okay, when we talk about mature chimpanzees. So we've got that third variable that we need to introduce, and therefore would have a 3x3 matrix. So we have a 3x3 matrix which is required. So having said that, this is our 3x3 matrix. We've got Jn plus 1, An plus 1 and Mn plus 1, and that's equal to this matrix multiplied this by this vector Jn, An and Mn. Okay, that makes sense. Now the difficulty in this question is determining this, what goes inside the elements of this matrix. That's the hard bit of this question. And for that you have to bear in mind the following statements. No new juveniles arise from mature chimpanzees. That makes sense because we know that a mature chimpanzee does not reproduce. Mature chimpanzees do not regress to adulthood, meaning that if you're a mature chimpanzee over the age of 40, you can't go backwards in age to adulthood. Hopefully that makes sense. And juveniles cannot proceed directly to mature chimpanzees. What that means is you can't start off as a juvenile chimpanzee and then go straight to being a mature chimpanzee. You have to go from a juvenile chimpanzee to an adult to then a mature chimpanzee. So hopefully those three statements make sense in of themselves. And if you use these three ideas, this matrix would make sense. And I think a good way to think about it is if you think about what would happen after the first year. And we'll do all this in blue. So we've got J1, A1 and M1. We have 0.6 B, C, 0.08 C, 0, sorry this is 0, 0 D and E multiplied by J0, A0 and M0. And if we write this as a system of three linear equations, J1, that's equal to 0.6 times by J0 plus B times by A0, and then we have no M0. A1, that's equal to 0.08 times by J0 plus C times by A0 plus 0 times by M0, and M1 is equal to 0 times by J0, and then we have D times by A0, and then we have E times by M0. Okay. So if you look at the equations like this, these statements make a bit more sense, and it makes more sense as to why we have these zeros here. So here in the first year, the number of chimpanzees, the number of juveniles is equal to a proportion of the initial chimpanzees and the adult chimpanzees. Okay, that makes sense, because what we're saying here, and if you go back to the question, this makes more sense. It's something that we said before. It is the proportion of juvenile chimpanzees that survive and remain juvenile chimpanzees next year. And essentially, it's this statement which we have to make sense of. It's using this statement in this question. So, because they survive and remain, that corresponds to this bit here. They survive and they remain. And it's the same thing here. It survives and it remains. So hopefully that bit makes sense as to why we have this 0.6 and this 0.08 remaining, because we still take into account those chimpanzees that survive and remain, and obviously that number is decreasing, so of course we still need these numbers less than 1, the 0.6 and the 0.08. Okay, hopefully that makes sense. And obviously adult chimpanzees can reproduce, so what we're saying by that then is if adult chimpanzees can reproduce, they can also produce juveniles. So the number of juveniles in the first year, that's equal to the number of chimpanzees that remain from the previous year, which is this bit, plus some number of the initial adult population. And obviously these guys are reproducing, so this guy is reproducing. Okay, and we have 0 if I add this in, we also have 0 m0, because these guys don't reproduce. Okay. So hopefully that makes sense as to what this first line means. So that's why we have this 0. Okay. That's why we have this here. That's very essential. This is the most essential bit we need. And then in terms of adults in the first year, well, this is quite interesting. We know that from the question that if you take a look at the initial number of adults, that was 51200, and then in the first year that number's decreasing to 43008. So the adult population therefore is decreasing. Okay, hopefully you can see that. So maybe if we mention it here, the adult population is also decreasing. And that makes sense, because initially we start from 51200, and then in the first year we go to 43008. So just bear that in mind for this next statement. The number of adults in the first year, that's equal to some proportion of the initial juveniles. And the reason we say this is these guys are growing up into adults. And then we've got the fraction of adults which remain, which is this CA0. So just bear that in mind. And you would also have to recognize that we have 0 m0, because we have 0 m0 because mature can't go back to adulthood. So that's why we have 0 m0 over here. Okay, so just bear that in mind as well. And the next thing, mature adults, that's equal to the number of that's equal to a proportion of adults that grow up into maturity. Okay, so these adults go into maturity. That's the DA0. And then we have this EM0, which is those that remain. Okay, so this bit is the EM0 is the bit that survives and remains. Okay, and the reason that we have a 0 J0 is because of what we said over here. It's because of this statement here. Maybe if I just copy and then paste. So this over here, forget a different color. Oh, let's get this. So this over here is because of this statement here, which is why we have this 0 here. Okay, so hopefully that entire thing makes sense. I know it took a long time to explain, and hopefully it's quite clear. If it's not clear, please go over it again and again and again what I've said. But you just have to bear in mind that these statements make complete sense with what you've got in over here. And I think if you think about this in context, it makes a lot more sense. Okay. So hopefully all that makes sense. And that's the end of the paper. Question 10 was the most difficult part of the question. They did not realise beyond parts A and BI that what to do further. Part A, a lot of people gave the incorrect definition. They did not realise that this idea of juveniles remaining as well. And we discussed that in the question. A lot of people found the first part of part B quite easy. It was just a standard inverse matrix question, but they made errors in finding out the determinant, and that was just sign errors. But overall, that was pretty well done. The next part was quite difficult to find out what A was. It was just a simultaneous equation question. But people question, basically people were failing to realize that they had to use the 64,000 chimpanzees to find out the value, to find out the values required. But essentially those who used simultaneous equations found J0 correctly, which is what we did. A lot of people fail to see the connection between part B, between this part and part B III. A lot of people did find the correct difference though, however. Part C, that was quite difficult. If you found the correct J0, then you found the correct explanation. But there were a large number of responses that were not based on the solutions from part B. And that's basically saying about how in the question we were told that juvenile decreases, but in part B we saw that it increases instead, based on our initial value of A0. Part D was quite difficult overall. Some people did realise that they had to use a 3x3 matrix, but did not know what to do beyond that. Many focused on trying to adapt one entry in the given system, either just in its value or by adding a variable based on the number of mature chimpanzees, while others attempted to adjust by subtraction or of an extra vector term. But a lot of people did not know what to do, and I think even I didn't know what to do, if I'm honest. I had to read over the mark scheme a couple of times to understand this question, but I think when I explained it, I think it sort of made sense what I said, hopefully. But if it isn't, I'll try to explain it again in the comments below.